ultraviolet and optical infrared studies. He's actually, our connection is that my postdoc Huy actually did his PhD with Daniel at the University of Massachusetts. Daniel got his degree from Columbia University in 1990. As I mentioned, he was at among others, he was a Hubble Fellow, which is a very high reward you get as a young postdoc in Boulder at the Joint Institute for Laboratory Astrophysics. He then, after a while, came to the University of Massachusetts, where he is now a full professor since 2008. Program with Chandra, actually 3 megaseconds observing time on the galactic center, which is quite a lot. And as we just discussed, millions of dollars into these observations. And yeah, I'm not much. Yeah, and before, also Daniel will be staying with us for a few days. He's invited by our group. He's here today. Tomorrow, I'm not sure. I think in the morning, and then at the beginning of next week, Daniel will be here as well. He's in the visitor office in the first floor, in the VIP office in 318. So please feel free to discuss him. He knows a lot of things, particularly, well, anything about the intergalactic medium, I guess, galaxies, nuclei, black holes. So Daniel, please.
Okay, thank you. Thanks for the invitation. And it's a really great pleasure to visit this beautiful country. And I so far enjoyed it very, very much. And as Ryan mentioned, and I work on different topics. This is a relatively new topic for me, and actually I try to avoid AGNs as much as possible in the past. But 3 years ago, I was on sabbatical at the Institute for Astronomy in Cambridge University, and I think something new to do, right? I was involved in this 3 million seconds Chandra a visionary program for the Glass Center, but I was involved mostly for the fuse study, gas, in the around gas center. But since nobody is really working on the black hole equation, most people interested in the flares to the multi-wavelength campaigns. So let's I volunteer to work on the equation towards the black hole. I think it's a very important problem because, as you know, almost all the galaxies, as major galaxies at least, in the universe contains black holes, supermassive black holes at the centers. Okay. But only a small fraction of such black holes are active, less than 10%. Most of the black holes are quiescent. It's very low luminosities. It's seem not doing much. But they are doing, of course, black holes have gravity or try to grab things towards the black holes producing energy. Okay, so if I don't see much, that means they're not doing much. Okay, but so for our galaxy, the center, because so close, even it's not doing much seemingly, but we can study very carefully to see what's actually going on. Why, for example, the black hole is so quiescent, and whether actually there's much interaction going on near the black holes. And as you, so these are so kind of over the last 3 years, we've really developed a large kind of a comprehensive program, not only for analyzing the data, but also in terms of simulations. Real simulations for first time, now we directly confront the simulations with the data quantitatively. So that's what I want to show you here. This is still very much ongoing work, but normally in the referee process of the papers submitted last month or so. So this is my student currently working on the project. This is the former student in Princeton, but now the Einstein Fellow at the Center for Astrophysics. And Jerry Ostrike, probably now most people now have the joint appointment at Columbia University and Princeton. And the Christopher Russell is a postdoc at NASA. And so also from our colleagues in Chile, and quite a few other people's involved here. So this probably is a kind of familiar picture of our glass center in the near infrared. You see a concentration of very young stars on a few million years old, which is by itself is a very mystery. Ryan certainly is an expert in this field. and on top of the concentration of old stars seen here in kind of orange color and the young stars in blue. But if I get closer to the black hole in here, and this is called A stars, which you can monitor the motions of these stars. That's how you figure out the mass of black holes, which turned out to be has a mass about 4 million solar masses, which is very well determined. But in X-ray, it's very, very faint. It's only a few times like a solar luminosity. And which is correspond to about 10 to minus 11 adding the limit, which is kind of upper limit for the accretion or kind of radiation a black hole of surface mass can produce, which can balance the gravity and the radiation pressure. But if of course the multiple energy is not in the X-ray, is in the millimeter and infrared, which actually add together would be couple of orders of magnitude greater, but still much less than at the limit. So our black hole, like shown here in even X-ray, does not stand out. So, but it's there. And now rough estimate, as I show, with certain temperature of gas and density, and you will find the boundary radius. But it's kind of characteristic radius where the pressure, thermal pressure of the gas balances the gravity. So within this boundary radius, so basically the gas will be under the influence, strong influence of the gravity of black holes tend to be pulling towards the black hole. So that is kind of characteristic radius for our black hole. This is RS13, is a nearby small clusters of young stars, which produce a lot of winds of young stars, produce a lot of fast winds. Fast winds collide with each other, producing hot plasma. So where people have proposed as one of the scenarios for accretion material towards black hole is this kind of shocked stellar wind materials, but it's never been proved. Okay, so and here is called a pulsar wind nebula. Is a pulsar which energetic particles when it's moving, they like produce a comet-like shape because of ram pressure. So this is known as possibly the leading candidate for TV radiation. People have observed for example, by Hess, and this is actually instead of due to the Sgr A star, it's most likely the pulsar wind nebula. But right now, it's because within this region, within the resolution of the TV observations, still cannot be distinguished firmly. So there's a number of questions we want to ask. What is the mode of accretion and the kind of this radiative inefficient accretion? The matter has to be falling towards the black holes because there's gravity always wins. But whether the matter actually just falling towards into the black hole with not much radiation, or whether maybe the black hole is not really doing much accretion, and in the process of flowing in, there's a lot of material also flowing out. Okay, so that's the different scenarios of the accretion process. So what actually determines the luminosity, the X-ray luminosity of the black hole? We still see a lot of debates over the many years if different versions of the radiative inefficient accretion flows. So what is the possible outflows? How the outflow interact with the surrounding mediums? Of course, black holes, this kind of interaction is very important to understand even galaxy formation evolution. We know the connection between the black holes and how the galaxy form, because there's a clear correlation, for example, between mass of black holes at centers of galaxies with bulges of galaxies. So hopefully, because we can have detailed view of our Sgr A star, so by answering such questions, we hopefully can understand the large or kind of silent majority of supermassive black holes in the universe. Okay, so that's the idea. So this is actually the actual data we obtained in 2012 for the XVP program, X-ray visionary program of Chandra. This is one of the first visionary program. This costs like weeks of spacecraft time and talk about many million dollars of investment. So this 3 million moving out of all the gaps between observations. So it seems to be continuous. And here you see the flares. These are the individual flares. here marked in the red lines here. There are many of them. So since we talking about flares, will be complete different talks. So I will not get into. We publish papers that is already published. So I will not talk. So let's remove all see the time intervals where you see the flares get quiescent emission. Okay, seen here. Of course, remove some time here. Okay, so also flares, by the way, you have the kind of still very interesting topic by itself. There's correlation between total energy of flares, of individual flares, with the duration of flares. There's all flares, the physics of flares still not understood. But somewhat like the flares of solar flares. Okay, so due to power, most likely to the kind of magnetic field reconnection events. So this is the whole, we have a whole different effort is try to understand the flare physics. Okay, we just complete a new detection and also for all data, not only 2012 data, but also all data before the 2012. And we have a very nice detection and we're currently doing a lot of statistics analysis. Now, let's remove the flares. But say, okay, you remove these flares, it's still weak flares. You cannot detect them individually in the quiescent emission. But you can make some constraint what possibly might be the flare contribution in the so-called quiescent emission. So this is a comparison for autocorrelation function of the light curve. So this is before removing the flare, you see a nice correlation because photons from the individual flares will be correlated in time. So this gives a time scale, which is a few kiloseconds, with how long individual flares will typically last. So this you see this very strong correlation of the photons before removing the flares. But now after removing flares, you only see barely some correlation, autocorrelation. That means the contribution from flares in the quiescent emission is very, very small. Okay, so where at a certain limit is less than about, at a maximum is 20% also. So another way, this is from the timing study, but another way to look at the spatial distribution. The chandra has this resolution about a half arc second in X-ray. So very, very, very good. So we can actually see the emission from Sgr A star is well resolved. This is a comparison of a quiescent emission, the radio surface brightness profile, with the flare image. The flare with brief comes from very center near the black holes. So look in the sky, look point-like. So this basically is a point spread function. So actually here you probably cannot see very well. We compare with the instrument spatial function here. You cannot really tell the difference. So flares almost like point-like, but you clearly see it's the logarithmic scales. Clearly see quiescent emission is resolved on scales greater than about 1 arcminute to few arcsecond. 1 arcsecond to the few arcsecond scales. So emission from Sgr A star is well resolved. Okay. Now we basically want to understand this quiescent emission. We also can set a limit on what is possible the point source contribution, upper limit from this study. So this is work done plus spectrum, very simple spectrum study, modeling which is one spectrum. So this work is published in Science a couple of years ago. So in that paper, we also show this removing the point source, which has a point spread function looks like that. It contours, and the image shows this quiescent emission after removing the point source. So clearly it is resolved, but also this elongation. And interestingly, that's that time when I noticed that the elongation is this orientation is similar to the called clockwise disk of massive stars, which discovered a long time ago. And so now which is kind of consistent with the stellar distribution, which is totally different things. But by connection with the winds, if as source of the accretion material, so this will be natural. But this are, of course, there's a very qualitative look. So say, okay, you see nice extended emission, which is have similar correlation orientation as a stellar disk, but we want to really prove it. And so why this extension, this elongation, why this symmetry? So that's what we want to do, is to do simulations. So basically, these are the quick questions we try to answer. Are the X-ray data consistent with this shocked stellar wind accretion scenario? Secondly, so what actually we can learn about this morphology, X-ray morphology, as well as density and temperature distribution of the accretion flow. And so what constraint can we obtain on other X-ray emitting components? For example, central point-like component we cannot resolve, but very close to the black holes. And what kind of influence we could have about the mass and energetics of outflows. But as long as once we have a consistent model, we can make the inference from the simulations. But we first have to prove that the simulations are consistent with that. Okay. And eventually we want to see how the Sgr A star activity changes with time on much longer time scales than individual flares, say over the last hundreds of years. So we can do that. So this simulation actually was earlier published ago. We kind of improved some old simulations. Most of the stars here, actually you see the dots here are individual stars, central black holes right there. And so you have to, these are the stars, you know the in sky the positions, but you also know the velocities, not the complete information about three-dimensional distribution, but you can give best guess. But this is as good as you can get realistically looking back in time, because you know the proper motion of these stars, and then resimulate the whole orbits back in thousands of years ago, started simulations. So that's basically what you've seen here. This is simulations over the last 1,000 years or so, how the stars moving around. These are not black holes, okay? These are stars, although they look like black. But the black hole is somewhere here, but you see the wing-wing interactions, because strong winds from individual stars colliding with each other at thousands of kilometers per second, producing basically tens of million degree gas. This is the plasma supposedly be capturing in kind of random fashion by central black holes. Okay, so this is kind of mess, but will be stopped somewhere. Okay, but this is basically one snapshot, a current snapshot. So after 1,000 years evolve, everything moved to the current configuration of stars. So now let's take a snapshot of X-ray emission current. So this is simulation without the instrument effect, no PSF, and no major burst in the past hundreds years ago, which may disrupt the accretion flow at all. If the Sgr A star had a major burst, of course, a few hundred years ago, which could destroy all the accretion flow. But it turns out that this no major flare simulation gives best fit to the data. So this are shown here. So this is after the PSF of instrument. So this is observed. Of course, there might be some similarities, but of course, there's features which not in the simulations. For example, this certainly says so this is RS 13, and this pulsar wind nebula certainly is not in simulations. Of course, simulation is always idealized, but we want to basically see whether, say, look at the spectrum of this simulated emission, how they compared with Sgr A star emission. We're not looking at the real accretion flow right in this 3D simulation, which is very, very difficult, because really you're looking at simulated colliding wind, so these are much larger scales. Okay, so we basically look at it now. Let's look at around the central black holes, say within 3 to 5 arcsecond annulus. Look at spectrum, how realistic the simulation might be compared with data. So this is actually the comparison. This is without doing anything. Okay, of course we have to adjust a little bit mostly the normalization within effect 2. Okay, so the bottom line, the spectral shape looks very, very good. Just simple simulation. Okay, from this colliding wing, you compare with data shown here. So this red curve shows basic simulation. Your prediction, of course, you know density, you know temperature at each point. Then you calculate what is plasma emission. So this is basically the brainstorm radiation plus line transitions and project in the sky. Then what you see here. But within factor 2, which is well within the uncertainties of simulations, because you have to assume certain wing velocities for a mass loss rate from each individual stars. Okay, so we think this is very, very encouraging, not a proof of the things. So now this is for this annulus of from 2 arcseconds to 5 arcseconds. Now we want to go to really inner regions. Now really look at this onset, basically how this is very near the boundary equation. This characteristic radius of the balance between the thermal motion and the gravity. But we now want to really look now into the equation flow towards the black hole. So this is done now in 2D because it's very kind of expensive. You have very large dynamic range from a few hundreds of thousand Schwarzschild radius down to about 100 Schwarzschild radius. So you're talking about many orders of magnitude dynamic ranges. So because you could do 3D simulations, but you cannot do the very expensive to do a set of them. But let's do the 2D simulations, which capture the all essence of the asymmetry. Okay. The key issue here is that we want to do 2D simulations, have a quantitative comparison with that. In a sense, really want to fit instead of just a qualitative comparison. Okay, so this is the first time we introduce basically now you have angular momentum. Okay, so without angular momentum, actually all this radiative inefficient equation flow is scalable. It's a very, very simple physics. You think about it, actually that actually attracts me into the field. Put a black hole, which is very simple, only 2 parameters here, mass and the angular momentum, which doesn't really matter much for this case. And the charge, we are not talking about charge. So this is only mass, putting in the hot gas. If you don't understand it, what else you can understand? Okay, that's my simple logic. Of course, this is a little more complicated. So if you say no angular momentum, you just do one simulation, everything is scalable, the same self-similar. Okay, you just need to know what is the boundary at the outer boundary, what is density, what's the temperature. So everything is just scale up and down. Now, with the angular momentum, the breaks degeneracy. Okay, so we need to do basically a set of simulations with different called characteristic circulation radius, which basically is radius which you have enough angular momentum, which the centrifugal force balances gravity. Okay, so that's basically a characteristic radius for the angular momentum of the flow. So this ratio to the boundary radius, okay, which depends on temperature of the gas. But then we just do a few simulations, say 3 simulations that can interpret between the simulations. So that's all you need. So this is a simple case for simulation to compare with data. Okay. Have you heard of any real simulations, a cosmological simulation you can compare directly with one realization of the universe? You cannot do that. But this is a really beautiful case. You can actually do the simulation of accretion to the black holes with that quantitatively. Okay, so this is one of the simulation. You see the density, basically 2D simulations, this is the polar coordinates, and so this away from the black holes, the density distribution and temperature distribution. Of course, temperature density both increases with the radius. Okay. Now, this is now how to simulate. We do have some parameters. Okay, so we input called this the Monte Carlo Markov chain hierarchical Bayesian analysis. But it's very, very simple actually. It's basically forward fitting. Okay, and with some priors. That's it. So basically, you have some basic parameters, high-level parameters, which is bounded at the temperature, density, and this circulation radius ratio. Okay, so these are the 3 parameters in simulation. You want to determine everything can scale, and this is the point source, which is not in simulation. Okay, but this is physics near the black holes. So this basically we assume a power law with the power law index and the normalization. This is the key parameters for everything. And now you basically from the accretion flow, which basically you can predict what is the theoretical counts. But to compare with real data here is in spatial coordinates x, y, as I and j, and different energy bands. Okay, we break the data into 3 energy bands. So we can use basically some spatial information and also some spectral information, okay, simultaneously. And of course, we have to account for the projection effect. Okay, here is inclination angle because you have angular momentum, so which flattens the accretion flow. So depending on the inclination angle, then the projection, the symmetry will be different. And also the position angle in the sky, okay, there are 3 parameters, and some background in different energy bands, and of course the right centroid. So this is very, very simple. Okay, so now of course you have to account for the projection effect. You integrate along the line of sight. This is also very, very simple because it's an optical thin case, just integration. And then convert with the PSF of the instrument, then convert the theoretical counts, photons, into the counts in the instrument that you detect. All these are instrument effects, projection effects. It could be well done. So basically now you do, you have these parameters, you can compare with the data, then you then revise these numbers and search for the best fit. That's all the ideas. Okay, it's very, very simple actually. Although implementation takes work because you have to optimize the parallel computing, make it fast. That's the only thing you need to do. So I will not go details, but this is kind of results best fit. So this is the model in the sky in 3 energy bands, lower to the high energy bands. This is real data. This is residual, the data minus data. So you see actually pretty good, at least in central half arc seconds also. Okay, it's very, very nice subtraction. It's as good as you can think of. This, of course, there's some features here which is not simulated, which in the projection from some extra external sources emission. We know it must be there. Okay, but overall, you see actual subtraction in 3 energy bands. A lot of data here. It's all constrained, but overall, it's a very nice fit. Actually, you can prove this is a nice fit. But here, just gave you this actually is the best fit. The 1 sigma confidence intervals, all the parameters simultaneously determined. With arrow bars here, this is the inclination angle of the accretion flow, and this is position angle and circulation radius, the temperature density at the boundaries. The background is not less, it's a nuisance, but it have to be there. And plus the very steep power law ascent. It's very, very new. So we got new information by modeling, physically modeling this accretion flow, the background, and then we now leave something there we can fit with that. This is new information about this is a normalization, which is basically the fraction of the contribution from point source. This is the power law index. It's very steep, it's bottom line. Okay, that's have a strong implication. So this is a geometry effect. Okay, so affects the projection. But this actually is these numbers are consistent with the so-called clockwise stellar disk. It's very nice. Just directly from, we have nothing, no information is used from the stellar astrophysics. But the orientation, inclination are consistent with what independently measured. So that's very, very encouraging. That's, I think, it's a very strong, if not proof, it's strong evidence for actually for the accretion flow coming from this shocked stellar wind material. So angular momentum is provided by the orbital motion of the stars. Okay. So we can of course say a lot more about the boundary. These parameters, the temperature is high, is what you expect from the gliding winds. So these are tens of million degrees. It's expected from kind of speed, or you expect from the stellar wind. And density is you can estimate now directly from models. This three-dimensional fitting, okay? And this actually is what you expect from simulations, from colliding wind simulation. And this actual number is kind of large than what simulation earlier predicted. But I think the simulation has its own problem because it's PH simulations which tend to have the angular momentum issues. We need to improve. Actually, I tend to believe our number better. So that's actually have strong implications for future modeling of the or even simulations. And so this is the very first time we estimated this circulation radius. It's very, because circulation is very important. Because of course this angular momentum tend to balance the gravity, which affects the density profile. Therefore, the spectrum, because at different radius, you have different temperature of gas. Because when you flow getting close to the black holes, the Fourier theorem tell you the temperature increases, winds decreasing radius. So, depending how much matter at each radius, which will give you different spectrum. So this here shows two basically illustration of the density profiles with two different angular circulation radius. So you see how basically the angular momentum affects the accretion flows. Okay. So this is now let's say a few words about point-like sources. The point-like sources we basically now first actually firmly about only 60% of the emission we observe in quiescent state comes from the point-like. This is very much unlike the AGNs. AGNs where almost 100% of radiation come from within, say, about 10 Schwarzschild radius. But here for this radiative inefficient accretion flow, at least in Sgr A star, this extreme case, most of the radiation comes from way out in more than about 1,000 Schwarzschild radius. Okay, this is thermal motion with line emissions. It's very much different from the normal AGNs. And so now for point source, we have lots of theories proposed. Could be anything. Could be brainstorm radiation because the electrons become so hot because so close to black holes, just converting gravitational energy into the heat. You could produce brainstorm radiation. It could be synchronous radiation. It could be acceleration of particles. And it could be inverse Compton scattering of relatively low energy radiation upscattered by the hot electrons. These are all the models. Now because the brainstorm will be very flat spectrum, we know. Okay, brainstorm have very flat spectrum. The synchronous radiation should have the same spectrum as you observed in the millimeter and in the infrared, which is flat, quite flat, and much flatter than our measured. So only thing left is actually the inverse Compton scattering of low energy synchron scattered by the hot thermal electrons. Maybe not a complete thermal Maxwellian distribution, but they have very steep spectrum while producing a steep inverse Compton scattered spectrum. So that's basically is only thing I think left. So I think this is the very most important implication of the work. Okay, so for the point-like source in the middle. So basically, we kind of eliminated these two possibilities, leaving only this as a leading scenario for producing radiation, point-like radiation from near the black holes. So this is very important for all the studies of radiative accretion flows of radiation from the near the black holes. Okay, so the topic I want to talk about is variabilities. Okay, simulation shows actually basically the accretion flow could producing rate could be changed with time on time scales about 100 years ago. Also, because the instability of accretion, because stars moving around, Okay? So when one starts getting close to black holes, you give the more higher density, so things like that. So kind of stochastic behavior. So actually there are evidence, there are lines of evidence for such variabilities from let's talk about that. Okay, so how can we measure it? In X-ray, looking at the nearby molecular clouds, you see strong X-ray radiation. We believe that it's due to reflection of the past activity of Sgr A star, at least one scenario for that. For example, this region, you see this is X-ray image in different energy bands. You get a spectrum of this region, which is this molecular cloud with a very strong fluorescent radiation in X-ray. It's an iron fluorescent radiation, neutral gas. So you see very strong 6.4 keV line emission. Another region, you see the bridge, it also shows similar kind of radiation. So people can say, you have observer down here, look at Sgr A star, you have burst some time ago, you start to now see the reflection from different molecular clouds, the fluorescent radiation. Okay? Now, depending on the location of these molecular clouds, you can figure out the history about the past activities of Sgr A star over the, say, last 100 years or so. So some cloud as a bridge region will show actually over the time, last 10 years or so, or 15 years or so, actually see radiation, the line emission actually increases with time. Some other regions is actually decline with time, now depending on the location of the clouds. This turns out the biggest uncertainties in this reflection, reverberation modeling. This again, people talk about reverberation all the time. But this actually, you have spatially resolved reverberation. You know, at least in the sky where the clouds are. But actually, the biggest uncertainty right now is the line of sight locations of these clouds. Okay? So one of the projects we have now is to map out this, to figure out the locations, line of sight locations of the clouds. So since this is the ERAM site, so I choose to force to advertise our telescope, which is jointly developed, constructed by our university and Mexico as a country. Okay, so this is supposed to be a 50-meter telescope, which already built. But right now the operation is on the panel, 32-meter panels are ready for has been doing observations over the last 2 years. So actually, this is also another part of called Event Horizon Telescope, is to map out the shadow of the supermassive black holes. This is the whole effort. But what I did is to map out the central molecular zones in 1.1 millimeter using one of the instruments called ASDAC. And this is actually map. My first map was the first large-scale map made by large LMT over 20 hours. This is degrees of the 1.6 to the about 1 degrees in 20 hours. So actually, to my surprise, it worked. Actually, it's surprising. So this is an image with the highest resolution now from single dish large-scale map is about 9 arcseconds. Okay, so when 50 meters, you think will be much better. In the next years, we'll be able to do that. This is a map. Actually, first time I'm doing the millimeter astronomy. So now, the famous regions, Sgr A star itself is very bright in the millimeter. We know it's not from dust emission, but the rest of it is clouds are from dust emissions. As this Sgr B2 star forming regions, supernova remnants. It's a cloud, a brick cloud, and Sgr arch cloud there, all in one map. Now, of course, ground-based observing, you need to remove the atmosphere. You have to filter out the kind of short spacing information because your skies keep changing. So we have to add a low resolution signal there. Fortunately, those maps are available from Planck, from the I think the Bolocan survey, which have much poorer resolution but perfectly matching to add the low short spacing information into. This is a combined map, 3 map, Frank, Borocam, and MT map. So beautiful, I think the most beautiful millimeter map ever produced for the central molecular zones. Okay, so I'm very much proud of that. So we can do much better in the near future. But that's information. So that's compared with the actually now Herschel data and also spatial data. So this is all together in 3 colors. So our map in red, the green from Herschel, this is 8 micron from the spatial. So you see actually they are very different looking. So right now we are doing, actually one student doing a very careful job. This is a Bayesian approach to study individual clouds, combine all the millimeter far infrared data together to get SED fit pixel by pixel to map out the dust emission or dust column density. Once we have that, we know where dust mass at each individual pixels. Then we can combine with extinction map. Okay, now independent map. Then we can figure out the 3-dimensional location because extinction depends on where the cloud is along the line of sight. So most of these clouds, the distinct clouds as we see in this map, is embedded in the stars. Okay, so once you know the dust mass, where they are, so you can just as prior, then not folding in the extinction information pixel by pixels. I think we can figure out the 3-dimensional distribution of these molecular clouds in the central region. So that's what I really want to do. Hopefully, some people here also can help out, is to get 3-dimensional picture about not only about the gas, because gas produced here, dusty gas produces extinction. So you want to figure out also stellar distribution. Okay, how stellar distribution looks like, whether it's asymmetry. You need to basically solve this problem simultaneously. Extinction, dust, and the stellar distribution, all simultaneous, as we have tried to do for the M31, for example, the larger regions. So that's basically the hope way try to. I will not have time. I should have only 40 minutes to give talks, but I think this topic is less important. But there's other ways to trace the past activities of the central Sgr A star based on the non-thermal, non-ionization equilibrium. There's evidence for that from the combined plasma emission. Okay, so of course the activities near the center of our galaxy affects the globally our galaxy. For the Fermi bubble is a good examples, which is now most people think is from some activities in the past, most likely the Sgr A star. And so combined together, we can actually start to form a history for Sgr A star activities from the reflection nebula, which traces history over the last few hundred years, to say now non-thermal, this non-ionization equilibrium jet kind of features are just shown. I will not get details about 10 to 5 years. And there's also some studies in the past about the ionization of the magnetic stream, which shows also over-ionization in the H alpha, which indicates some burst of UV radiation, or on time scales about millions of years, and on the few million years scales, you have Fermi bubbles. So we see in the past, Sgr A star most likely was much more active than at the present. Since declining with time, at the present is very inactive. But who knows? In the next 10 years, something might maybe happen. Okay, so that's the message I want to pass. So we really want to get a quantitative science by confronting real simulations quantitatively with the data, with extreme data, large investment in space craft time, to first to figure out, to see whether actually the data are consistent with these models, but also to figure out new physics, especially for the angular momentum, inclination angles, which will, once we have this 2-dimensional fit, then we have best fitting. We can start to do 3D simulations, real MHD simulations, because we know where the parameters are. So since it will be not as expensive as you have to explore all the parameter space. So once we have, say, MHD simulations, we can make calculations, make further comparisons with that, at least with limited space. And then once we have that, we can do, for example, to calculate the Faraday rotation measurements, which is a mystery for, say, the A star, very, very large. Then we can figure out how the magnetic field works. Okay, how the instabilities actually works in the accretion flows. And we figure out the three-dimensional distributions of the dense dusty gas, as well as the stellar distribution, and hopefully also the star formation history of the stars in central region, not only in central clusters, but on much larger scales, say within the central molecular zones. That's, I think, and of course, for the modeling of all the high energy activities which you observe in the center of our galaxy. I think I'll stop here. Okay, thank you very much.
Thank you very much. Are there any questions?
Daniel, thank you very much for your very interesting and exciting talk.
Yeah.
You mentioned that you get in simulations you get densities of order of 200 per cubic centimeter,
Yeah.
and temperature of order of 10 million.
Yeah.
So how can you sustain these plasma, such high temperature, such high densities?
So this basically is the idea from, because it's a young massive cluster around supermassive black hole, okay, which is a mystery, okay, how the cluster was formed. But once we know this cluster of the young stars. We know young stars emit strong winds, fast winds, wind speed about, say, a few hundred to 1,000 kilometers per second. So when you collide these winds together, shock it, you're naturally producing the temperature about a few tenths of a million degrees.
But the gas, say 200 per cubic centimeter, isn't that's included?
Yes, so that also it be naturally from simulation because of such a concentration of young stars. So you lose the mass, individual Wolf-Rayet stars will lose mass something like 10 to minus 5 solar mass per year. Okay, so this is a lot of mass. So actually, you collide it, you shock it, then basically you have ball of hot gas, which of course is not a perfect uniform. So what the number I get here is kind of average. Okay, so but once you get into the flow, probably doesn't really matter much. The other near the boundary, the outer, the boundary radius, the density probably not very uniform, but on average is about right. About 100 particles per cubic centimeter.
Okay, the second part of my question is how reasonable it is that you consider this to be optically thin when you integrate to the language?
Oh yeah, that's easy to calculate because this actually density it's kind of high, but actually is very penetrating. So as the cross section for the scattering is very, very small. So its optical thing is very, very good. Because the volume is not very big. Okay, if this kind of density, if to the galaxy size, could be a problem. Yeah, I'm actually basically since I normally very much encourage questions. Now this is part of my research. I do the radio work, as you mentioned, galaxy scales, halos of galaxies. I do the infrared work. Little bit, and mostly glass center, and you see a flavor of my millimeter work, and so I mostly spend time on galaxy scales. Any people who are interested talking to me, I'll be interested in interacting with you. Yeah.
So I have a galactic center question.
Yeah.
What happened? I remember there was in the first Chandra observations of Fred Baganov et al. There was this kind of jet-like feature to the west of Sagittarius A star. Do you see any of that in the 3 megasecond
No.
HVP observations, you know, this streak that went to the southwest
Yeah, southeast probably.
or southeast.
So southeast, right?
Yeah,
This is
so
actually one
I
of.
didn't see it in your. So is that?
Actually, it's a little beyond what my map shows.
Okay.
Which another former student published a paper a couple of years ago, showing it's linear feature is there.
It's still there.
But I'm not particularly convinced it is a jet from Sgr A star. I mean,
Sure.
but it's a linear X-ray emitting feature, which is beyond the map I showed.
Okay.
Yeah.
Okay.
Actually, the map that you show from the data from the LNT,
Mhm.
very, very interesting maps. I've been myself on top of the mountain in the LNT, a very impressive telescope. Let's see when it is fully working the whole surface. It will be very.
Yeah, I'm totally. I had some proposal also on Iran, although my fault it was not very successful. Actually, we want to take some spectrum on Perseus clusters. I didn't realize Perseus, the black hole, is not much brighter than say 10 years or 20 years ago. I just used older flux from AGNs. Now the spectrum is completely swamped by the continuum. So that's my only experience with ERAM. Because ERAM has a different spectrometer which covers I think the 1 millimeter window. So our actual spectrometer actually covers 3 millimeter window. I think it would be a nice complement data set, and both actually our MT spectrum and the ERAM spectrum will swamp completely become useless. But I look forward to other possibilities to really collaborate. I'm starting because of our telescope there, so really want to explore how to have a synergy of different instrumentations. Although I think telescopes are on the northern hemispheres, you kind of looking at the same target, but you have different instrumentations. Certainly will work beautifully. For example, I have been proposing a monitoring program for the Sgr A star. I didn't have time to show. Actually, we monitor 1 millimeter variabilities, and I think ERAM has very nice detector with even polarimetry.
We have someone doing a monitoring program here.
Yeah, I know. So I think it would be very, very nice to communicate how coordinate this effort. Using take advantage of different instrumentations on different telescopes, and there's a lot of things that can be done. And I think real MT, to my surprise, over the many years had problems, construction problems because lack of funding, things like that. But all of a sudden, they say, let's back to work even with 32 meter, and put everything together. You observe it, that actually immediately become useful. So that's just a very nice. I didn't do anything. My colleagues mostly who provides expertise and real instrumentations, real make it work. Yeah.
There's another question I'd like to have. I'd like you to comment on the fact of the accretion efficiency. You show that the activity now is very low for the 10 to 33, where by reverberation or 100 years ago it was 10 to the 39.
Yeah.
So what is this telling us about the? So it shows that it was 100 years ago much more efficient than it is now, which is very low efficiency, the accretion flow. What is telling us about the mechanism, or what produces the activity, the burst of activity on the scales of 100 or 1,000 years, which is now so low, the activity?
Actually, this part of work, theoretical work, is still very uncertain. Although I show this simulation, but this simulation itself has some issues because SPS simulation, whether this is a numerical effect or something truly in nature, you have this kind of, because remember, the accretion itself actually, because the colliding wing is not very, it's time variable. The stars are moving around, Okay, so you have climbing winds. If one star region happen to be close to the black hole, you have density could be very much enhanced. Also, in the climbing wind, you also tend to form cold clouds, like a G1, G2 clouds, which could be formed in such a maybe say debate as whether it's stars or clouds. But simulations you do see, at least in such a simulation, you do see formation of the dense clouds. So if dense clouds happen to be at a certain time dropped into the black hole, then it will have produced bursts.
So the physicity will be directly related to the actual
accretion rate. So once actually this critical rate, actually once say something like 10, greater than about 10 to minus, actually the simulation I showed here, 2D simulation, is actually initially for this purpose to determine at which point of accretion rate the efficiency of radiation becomes important, become more efficient. So something is the current understanding is about 10 to minus 2 at the limit. Okay, so if accretion rate is below say 10 to minus 2, then the radiation is most inefficient. But once if you have a cold cloud forming disk, then the angular momentum loads very, very fast, then the radiation becomes very efficient. So this can come and go. So basically now the center of our galaxy provides special resolved laboratory. Basically you can do special resolved reflection. Not only say look at time change, but you can actually resolve the emission from individual clouds, to see how actually they do the reflection. It's really, if you know the three-dimensional picture locations of these clouds, you really can pin down exactly what time the photons are rising, and then you see actually the flux is changing with time over just say few years of time scales. It's really, you cannot do possibly to do such things in the past.
So observationally, the length of the last burst, is there any limit? I mean, it was about 100 years ago, but is there any kind of constraint on the length of this last?
No, you see the upper down, so that means actually is changing. So one cloud you see bridge region, you see probably this arriving time. Basically, this if the location is really there, that means the burst is started. Mm-hmm. And here you look at this. Of course, this is a closer region. Now you see, because that means.
What's the time scale there?
This is yes. This is from 2002, 2010.
Now 10-year time scale.
10 scale. You see a change. So basically, you see it rising and fall. If you have more clouds, you basically now. Of course, you can two clouds difficult to tell exactly the profile. If you have more clouds, it means more sensitive observations, especially in the future, like Athena. Mm-hmm. You can really map out in all the reflection, especially, and you have three-dimensional picture of these clouds. Then you can really see how actually, because it's just right travel time. Yes, it's very, very simple.
Any more questions? So Daniel is going to be around here, so please go talk with him. And thank you very much.
Thank you.
Very impressive that you can model the accretion flow and it fits nicely.
Actually, it's very simple. Actually, as simple simulation as possible, especially for the